All right, so I'm Julian, like Hetty just said, and I'm going to be diving deep with you today into electrical engineering. And forgive me for just shamelessly plugging my university. All of my slides are in the set that they give me to present to industry. With the beginning of this lecture, I'd like to ask, when you think about electrical engineering, what comes to mind? I assume that it's electrical circuits or robots, and I'd just like to see your responses in the chat. Or if you like, you can just go ahead and use the yes or no response in the participant screen to let me know if that is essentially what you are saying, what you think it is. All right, computers, I get from Teddy. Anyone else? I'm only going to spend about 10 seconds on this. Yeah, electronic devices, very good. Okay, well anyway, my story is that that's essentially what I thought I was getting myself into when I applied to University of Illinois. But I was very much wrong. It's a lot more than that. And in fact, the person that convinced me to come here and study electrical engineering described the field like diving deep into a pool and never finding the bottom, which is where I get the title of this talk. Robots, exactly. Wires and stuff. It's great because it's actually like nothing like that. And in fact, I've completed a bachelor's degree and now working on my PhD, and I've managed to not make one single circuit and not wire anything outside of what I actually wanted to do on my own time. So as an overview of this talk, my goal is to essentially inform you exactly what an electrical engineer can do, because it's so much more than that. I'm also going to define the fields in comparison to other STEM fields, specifically with regards to mechanical engineering, material science engineering, computer engineering, and physics and math, all of which I assume you may be considering if you're looking at electrical engineering seriously. We're going to just look at two major applications of electrical engineering that I think are really important for modern technology. And then also what you can expect when you're pursuing a degree and career in this field, specifically courses and accreditation, and what you need to look for when you're choosing a college. So to begin, we're going to define the field. What is electrical engineering? And to do that, we have to first talk about STEM, which if you don't know is science, technology, engineering, and mathematics. Very common acronym when used in describing this sort of stuff. So science, I would describe, is studying the world. So like, finding inconsistencies in nature, sort of looking at how we understand things and critiquing and fixing that. Technology is more or less taking what we know and then making products for people to use. Engineering, where I am, is taking knowledge from science and then using that to invent new things to make humanity better, life easier, what have you. And then math, very different, I should say, from what you may be experiencing in high school, is more of finding patterns in the world or in other forms of math and then using your mind sort of to model them in a more efficient way. And where this sort of interfaces with itself is you start with math, where you may discover calculus if you're Newton or something like that. That then enables science to better formulate physics or chemistry. You don't have chemistry without a topic like group theory in math. I don't need to go into what that is, just trust me. Or something in that line. With an understanding of physics or with chemistry or with biology, you can use that to engineer a new product. Drugs, for example, is bioengineering. Understanding electricity lets you make electrical devices and so on. Cars need to have an understanding of thermal physics and whatnot. And then from there, you go to technology where you actually sell the products, you actually teach people how to use it. I'm not going to be talking about that at all because I basically have nothing to do with it. And then where exactly would I put electrical engineering with regards to other engineering fields and with regards to math and physics? So I have this spectrum, and I would say that electrical engineering veers very far on physics, where you basically have to understand quantum physics down to a T in order to get anywhere. But you also need to have a pretty good understanding of math. You have to have differential equations down, you have to have linear algebra at the very least. And then a little bit closer to math, you may put computer engineering, where you're actually working on building the computers, deciding how they process information. And even more closer to math is computer science. And some of my friends in computer science would actually just describe it as applied math, where you're basically telling a computer how to do mathematical equations. Worth noting is that several of these, or several colleges now just group all three of these together, and you basically decide for yourself, what do you want to do? And you will then sort of take courses that put you closer to physics or closer to math. Be that as it may, I still felt that this was important to show the distinction because it's still very much the case in academic journals, and a lot of universities do this as well. And the y-axis, if you will, here is classical versus quantum physics. Classical physics, of course, is something like figuring out the energy when you roll a ball up a hill and then watch it roll back down, or throw something in the air and see it come to the ground. I would put mechanical engineering much further into classical than quantum because you're dealing with heat, you're dealing with torque, a lot of very much classical physics. And then I put material science a little bit closer to quantum than electrical engineering, where if you're not familiar with material science, is something like designing the actual material a product will be made out of. So carbon fiber was a classic material science problem. Any sort of steel beam or a knife blade, or even things like polymers, what you make plastics with. That's all material science, and that really deals a lot with quantum. But electrical engineering, it really is sort of in between that, where you kind of have to understand a lot about classical to understand light, but you also need quantum to understand light. You need to understand how to make an antenna, which again uses both. And in my own work, where you may need to know Brownian motion, something that Einstein invented, or not invented, but discovered and just sort of proved, you need that. And then also something like Boltzmann statistics, which shows how gases work, more or less. I'm going to be talking in ways that would make my professors very unhappy, just as a generalization, but it's much easier to speak in these terms. So anyway, you may be asking who actually studies this stuff, like who cares, right? I would say that you need to be passionate in about math and physics. Specifically, you want to be able to take knowledge from different fields, different classes, I guess you could say, or different lines of thinking, and then using that to actually solve real world problems, and then also maybe think up new problems that you may not even realize. That's a very classic Apple ideal, that you think about ideas, problems in the real world that people don't realize are problems until they're already solved. And to be an engineer in general, you need to be driven to innovate and create, and you really should be moving to improve the world for everyone. I would say that the biggest mistake when you see people entering engineering is thinking that it's the best degree to make money. And while the pay is definitely good, you will be absolutely miserable if you don't find this interesting. It's not worth it to just go into a major, and this applies for any college major, to just go in there to make money. You really have to be passionate about helping people, and also designing things that are useful, not only just for everyone, but just for the future. And I don't want to understate how difficult these problems are. It's important that you're comfortable, looking at something that seems impossible to solve, and then within a couple of weeks, you'll be very comfortable knowing how to solve it, where you may see a circuit diagram, in my case, with 1,000 components. And then, when you first look at it, it looks like something you'll never be able to understand. But then by the end of a course, perhaps, it will be an abstraction, something you don't even need to think about to know how it works. And moreover, I would just say that you need to be ambitious and ideally be someone that wants to be a leader. And so, for example, oops, sorry. Satya Nadella, the CEO of Microsoft, studied electrical engineering. Rich Templeton, Texas Instruments, which, by the way, doesn't just make calculators, they make chips that go into just about every electrical device that you can buy. Mary Barra, who is the CEO of GM, of course, co-founded Apple with Steve Jobs, electrical engineering. Ginny Rometty, who was the former CEO of IBM, or is now the former CEO. She was the CEO for 9 years and studied electrical engineering. Replaced by Arvind Krishna, who, you guessed it, studied electrical engineering. And of course, Jeff Bezos, oh my bad. Jeff Bezos, the founder and CEO of Amazon, also studied electrical engineering at Princeton. Whether you like it or not, he studied electrical engineering. So that's cool, but what do I actually do with this? Well, before I get into that, I need to talk about a couple of size comparisons, just because I work very much in small things, and a lot of electrical engineering deals with very small things. So just go ahead and look at your hand, and I want you to just sort of pinch this. That there is approximately 10 centimeters, or a tenth of a meter. Go ahead, I'll give you a second. Okay. A tenth of that is about the thickness of a dime. So that's about a centimeter. A tenth of that is about the point of a pen. And then a tenth of that is about how thick your hair is. Go down another 20 and you get to red blood cells, which again, you're never going to be able to see this. Go down to 1 micron, you get a virus. The coronavirus is actually 100 nanometers in diameter, which is part of the reason it's so difficult to handle because it's so much smaller than most viruses. You go down to 10 nanometers and you're talking about gold nanoparticles, which is basically the smallest you can formulate gold easily. My bad. And then a little bit smaller, you get into carbon nanotubes, which is a form of carbon where the actual carbon atoms are able to form into a rod, get a tenth smaller, and you get to benzene rings, which if you've done anything with organic chemistry, you'll know what I'm talking about. If not, just assume it's really small. And then even smaller than that, about an angstrom. If you're in Baldwin's class, you'll know that a water molecule is around that size. These are some very basic conversions. I will be referring to micrometers as microns and nanometers very regularly through here, or I at least was planning to. We'll see what happens. And the second thing I want to talk about before we move on to applications is bits and binary in general. This is something that I learned in my first year here and kind of blew my mind in that you use computers and you don't really know how they work, I assume. But basically the way that computers handle information, and for that matter, any sort of electrical device, is taking information. So that can be sound, it can be pictures, it can be, words, it can be anything you can think of, and represent them in terms of powers of 2 added together. And that will then index something, and then adding those together, you can then basically have any book or any representation. And so what do I mean by that? So right here is a byte, which is just 8 bits. And with that, you get every single letter in the alphabet, every character your computer can produce. It also gives you most of the color that you can put on a screen. Usually now you need a bit more than that, but in the early computers, that's where it was. And so just think about that for a second. I'm talking to you through a camera, which is picking up my image, putting it over a silly overlay, of course. And then that's being put into ones and zeros through the computer to your computer. And then those ones and zeros still mean something. They're then being used to reconstruct what I'm saying and my picture so that you can consume them and then hear them as real sound. It totally blew my mind when I learned this, of course, because this is just like the baseline, of course. You don't necessarily understand that every bit of the virtual reality is just a 1 and a 0, no pun intended. So just think about that for a moment. And if you have any questions about this, I'm happy to answer. I'll open up the chat. Very good. So exactly what do I mean by a bit being sent through here? Well, I'll talk to you a little bit about signal processing, which is the bread and butter of electrical engineering. And essentially, when you want to communicate a byte over a computer or anything, what you'll do is you'll put it in the string with other bytes. You'll make a time segment that will tell you how long you have to read something. So you can sort of think about this as a flashlight turning on or off. You're looking at the other side of a field, someone's blinking a flashlight, or maybe even smoke signals. That's really the closest analog that I can give to you for this. It's basically high-tech smoke signals. And you basically will turn on the light and you'll get a 1. And then if you wait a certain amount of time and there's nothing, then it's a 0. And then you string that together with billions and billions and billions of bits, you get billions of bytes. And then that is how we actually are communicating here right now. So again, this is like so far away from anything that I assume that you're learning in high school. I'm a bit out of it now. I graduated in 2014, so I don't know what they're teaching you kids, but this to me was very, very far out. So like I said, you basically have these bits, they get put into the computer, and then you're able to process them into different pieces of information. So in this graphic, it's different lights, but just worthy of mention is a Snapchat. You can take a picture, that's being stored as bits, it's being transmitted over the cellular network, it's being picked up by another phone, it's then being turned back into a photo or an image. Don't need to get too philosophical there. And then that's being read up as a picture that someone else is reading, of course. All of the Fortnite dances, right? They're representations of people, but at the end of the day, they're just ones and zeros. Memes, of course, are just ones and zeros. They're just pictures that you can put on the internet, which we'll be talking about briefly here. And that, of course, is just ones and zeros that are communicating something else. And like I said earlier, this Zoom meeting itself is binary. Again, it seems very abstract because you think that you can just talk on the phone, you can video chat, but in reality, it's being sort of transmitted through this line of ones and zeros for us to actually talk. Any questions on this? I just want to make sure everyone's understanding this before we move on, because it's not going to make sense otherwise. I can go slower as well. Anything? Okay. Hold your silence if you understand. So now we're going to talk about the internet. And this is sort of representational of a classic electrical engineering paradigm, the black box idea, where you have something you have and something you want, and in between is a black box. And you can sort of reduce all engineering problems to this, that you have a desired result, you have something that you have, and something has to happen to change what you want or change what you have into what you want. And so in general, you may interface with the internet with a smartphone, a computer, even your car will actually, I assume some of you have cars, perhaps not, will dial into the internet. And that's how you get access to maps, to Instagram, to Wikipedia, and hours of PewDiePie. You know, so what exactly are we doing when we're using the internet? Well, it actually turns out that it starts with lasers. And I just want to, again, get a quick show of hands. Is this what you think of lasers? Is it a, you know, classic cliched, you know, plot element? Is it a blaster from Star Wars? Maybe there's a French guy dancing through a maze of them in order to steal some diamond or something, or maybe Iron Man's using it to kill some aliens. That at least to me was where I was in high school, and it's interesting because it's so far from reality. Yeah, okay, so I'm seeing some people saying that that's what they think of, some yeses, yeah. So it turns out these are all stupid and actually have nothing to do with lasers. Sorry. Basically, what you do in order to transmit the internet is you go ahead and you take a laser and you pulse it really, really fast. How fast? Usually like picoseconds, femtoseconds. So how fast is that? That's, you know, less than a billionth of a second. That's how quickly you're doing this. You're then putting it through an optical fiber, which you may have heard that word you know, used here and there. Basically what it is, and this is like the most science fiction thing I've ever seen using in the real world, it's basically glass that is being melted extremely carefully, you know, within a fraction of a degree accuracy, being pulled very, very delicately, and then stretched over several kilometers, up to 300 kilometers before it needs to be cut off. And then basically cased up, and then that's where you have this fiber. It's stretched out. And how thick is this? It's less than a micrometer. So if you remember the scale there, that's, you know, just a couple of viruses thick, more or less. You know, very, very narrow, much smaller than your hair. That laser is then being put into the fiber. It's sort of doing this tunneling, bouncing off the walls thing. I don't really have time to get into the physics of why this works. You can just take me for face value. That light is being transmitted in here and then coming out the other side almost unscathed. It gets a little bit less intense. And so what you have to do is basically put amplifiers every 300 kilometers or less, depending on what you're transmitting. And that's actually how you get these bits shot across the internet. This is at the speed of light, of course, because lasers put out light. Light travels at the speed of light, obviously. And that's really, I mean, that's as best as I can describe it, you know, at face value. And once you get past the amplifiers and several different nodes of the network, which we'll talk about in a moment, what you'll do is you'll read it out and then basically, like I said, repurpose those bits into information. So yeah, that's, you know, this is really cool to me. And I find that it's a little bit disheartening that people don't know that they're basically causing thousands of lasers to fire off every time they turn on the internet. And not just thousands of lasers firing off, but also, you know, basically a circulatory system worth of fibers across the world to fire off potentially. So what does this look like at a larger scale? Well, I went ahead and actually looked up what the networks are between me and you. My bad, I'm really bad with my mouse sometimes. And so I'm talking to my computer. Just forgive me for not having every bit of it here. That's going through an Ethernet cord into a modem. Then from the modem, you will be it's plugged into an optical fiber. That's then brought into the Champaign network node. I'm in Champaign, Illinois right now. That then is put into another optical fiber to an amplifier. And what does this amplifier do, by the way? I forgot to mention, the signal gets weaker. Basically, it loses a little bit as it's going through these fibers. And so what the amplifier does is it reads it and then just makes it, much, much more intense, much stronger, so it doesn't lose any information on the way. Of course, there's still a little bit of information lost. That's why you may have lag or, a website failing to load, that sort of thing. Anyway, so from the amplifier to Chicago, then to several more amplifiers, all the way to Zoom. Of course, the Zoom server has to get this information somehow. More or less repeat this hundreds of times across the country, all the way to Albany, and then to your local network, and then back to your computer through a modem. I'm simplifying this a lot, but what control systems are about, which is again a very big deal for electrical engineering, is basically deciding how do these different nodes communicate. There's information that has to be processed. There's information that is stored in different locations across the world. Certain data may be stored in a server in California. It may be stored in Europe. By the way, fibers run under the sea now across all major oceans, actually. That's how we're able to actually do like a Zoom call with someone in Europe without it being very laggy. So you have to figure out like where is that information stored. That's usually going to a server to figure out where the information is stored, and then that data is being routed to that location and then being accessed through the same stream backwards. And so it's a whole area of research. It's kind of like an incredibly convoluted and difficult Sudoku puzzle where you have to, instead of using basic math, you have to use differential equations, calculus, and all sorts of other things I don't want to get in here. But that is, again, a very big discipline for electrical engineering. I hope this is interesting to you. The next one I want to talk about is...
sorry to interrupt. Do you have a question?
Very good. That's a great question. I am not really the right person to answer it. The question is, how does the safety of security of information relate to the transfer of info in a control system? That is like a huge deal right now, and I'm super not the right person to ask that. I don't know. What I will say is that it's incredibly easy to basically stick your finger into one of these streams of information and take off the information, which is basically what Mr. Robot's all about, if you've watched that show. There's, again, a lot of research being done into how to protect this data stream. But it's obviously not 100% working. It's very easy to lose your personal information online, and this is in part because of that, or this is the cause of that. So yeah, a great question. I'm more of a physics guy than a control guy. I don't know the answer to that perfectly. I could get back to you if you're really interested. Basically, the answer is there are a lot of security measures that I didn't include. Basically, how the information is being processed at the network, that's pretty big. Also deciding who gets to access or put information through the line at each node as well, to basically have a readout of the address. You may be aware of your IP address when you log onto the internet. That's why VPNs, virtual private networks, work. It basically is saying I'm actually at a different location in the world. That's where my address says I'm coming from. And that's something that's definitely an area of research, but I'm more or less just stalling and saying things that I don't really know what I'm talking about here. I'm not an expert on this. I can answer any questions about physics though. So anyway, no other questions. I'm going to move on to facial recognition, which is an amazingly cool technology, if a little bit questionable in its ethics. Basically, how it works is you are reducing the face, this is a great image, to a grid, actually a matrix of information, and you're basically sorting the different regions of the face into parts of information that you're storing. More or less, you will use lasers to actually amplify the signals you'd be getting off of the face, and then you're able to take that information and basically store it in a very compressed manner that will let you read whether or not it's the correct face or not in the future. Something you may notice about facial recognition, if you don't use it very often and your face changes, it's not going to be as accurate because it basically relies on taking pictures of you multiple times in a given time period. And if you change significantly, it won't work. But if you slowly, like I am, growing a beard or something like that, and you do facial recognition every day, it will actually follow the beard. But if you just do it at the beginning and then at the end, it won't recognize you necessarily. And this is part of machine learning and a lot of other signal processing things as well. So how do you actually get these lasers to fit in your phone, right? It's kind of a crazy idea that those things I was talking about for the internet are also in your phone, right? Well, it turns out it's an infrared VCSEL. What's a VCSEL? A vertical cavity surface emitting laser. And this is like hot topic #1 in my field, pretty much. It's definitely up there. I'm not going to go into how it actually works. If you want me to explain it, I actually do know how it works pretty well. What you need to know is that it's this sort of cylindrical thing, and it is extremely efficient at producing light. So there are, thousands of them in a millimeter squared area. Again, a millimeter, about the thickness of a dime. And if you have an iPhone, you can actually use this diagram to show or to see where it is. It's called a flood illuminator, but really what it is it's thousands and thousands of these VCSELs in an array. And so when you take a facial recognition picture, it's not so much a picture as you're getting shot with thousands and thousands of IR lasers. You may be thinking this is really dangerous, right? I'm getting hit with lasers. No, it's actually super weak. And this is a different frequency or wavelength, if you like, than something that would actually be harmful. It's also significantly weaker than the sun in most cases. And then basically that information is being picked up by an infrared camera, which looks like something like the VCSEL array that I described, but sort of in the reverse, where you have a lens to spread it out a bit, and then also process the information and store it like I just said. The facial recognition for signal processing side is a little bit different. You're getting all of these ones and zeros. Basically, it will read not so much a 1 or a 0, but like what is the intensity of this particular pixel on the face. That's then put into a matrix, a two-dimensional array of information. And then what you can do with some computer science stuff, and I'll leave Sam to that, is basically decide which regions represent which parts of your face. Like, where is the eye? Where is the nose? The same process happens with the retina. You have your irises basically have patterns, and you can read different regions of the iris, and then that has a different frequency response when you hit it with IR, and then it reflects back into a camera. And a lot of signal processing is just about figuring out, like, how do you handle all this information in a way that makes sense, and how can you find the sort of pattern of a face to be relevant, and store for over time. How does a face change? And like I said before, if you stop using your facial recognition, it will become out of date because your face changes whether you like it or not. And the technology requires that it's constantly being updated. I'm not going to get into the ethics of that again. I don't have any comments officially, but that's basically how this works, where you have to constantly interact with it for it to actually know what you look like. But again, it's not so much like recognition so much as it is able to compare ones and zeros today to what it read out ones and zeros yesterday, and have an idea of the spacing of your features on your face. So yeah, I hope that's pretty interesting. I don't know. What exactly, I'm gonna move on to like what it takes to do this, because obviously this hopefully was interesting, but it's definitely difficult. I can assure you. What exactly does it take? Well, I would say it takes just about everything you can give it. So what exactly do you have to study to start? You have to get through calculus 3. So that's multivariable calculus. Most people see that and their stomachs turn. I love it though, it's awesome. You also need to get through differential equations and linear algebra, and also some statistics as well. What is differential equations? That's the study of change with respect to other change, more or less. Linear algebra is that matrix manipulation that I was talking about with facial recognition. Then you'll also have to get through several physics courses, and I'm also sort of condensing this. There's a lot of other science that you have to do. That includes classical, electromagnetic, thermal, and quantum physics. Classical, I already talked about. Quantum, I already talked about. Electromagnetic is any sort of light, basically. Light or any sort of field that you can't see, I guess is a way that I can say it. Anything that's involving charge, which is a bit of a concept, a bit of a abstract concept, I'm sure, but I'm happy to explain it if you like. And then thermal physics is sort of the study of heat, as you'd guess. And then you also need to get through several electrical engineering courses, of course. That's no surprise, I'm sure. The basics of these are circuits, computing, signal processing, fields and waves, which is, again, those electromagnetic things, semiconductors, which is a very specific type of matter that you probably have heard about in chemistry, but don't really know like what silicon does, what those different things do. Digital systems, which again is sort of fitting in that signal processing area where you're taking in information and processing it, or you're basically figuring out how to run information through a line of different systems. And then also basic circuit design. Like I said, I didn't actually have to make any circuits, but I did have to design several. And that's really the basics of what you'll have to do with the course. But this is really only covering through junior year or maybe even sophomore year if you're a bit ambitious. Most of the coursework that I had to do and that I remember is actually getting experience and lab work done in the things that I was describing. I also have lots of other applications I can talk about that I had to actually go in and learn about. You don't necessarily get that in high school where you can actually go and build a radio from scratch. It sounds like sort of wild, you know, at your point in your life, I'm sure. I learned how to build a microprocessor from scratch. Like, wow, I don't know. That's really cool for me. So that's the coursework you can expect to do. And it's more or less similar for other engineering stuff. And then something I just need to talk about because it's really important and isn't taught at like a high school, or isn't really, you know, you're not really aware of it in high school, at least I wasn't, is the importance of accreditation and certification. In the same way that when you're applying to medical school, you may look at like what is the acceptance rate for medical school. Equally as important for engineering is Abbott accreditation, which is sort of a bureau that just decides what does an engineering discipline need to be able to be useful in the field. And so they work with actual industry members to decide like what do you need to learn to get this degree and it be meaningful. It's super important if you're just going to get a bachelor's and go and get a job. Like if you go to a non-Abbott accredited program and then try to get a job, it's likely that if it's a large company, they won't even consider your application. And that's okay because most engineering schools are actually accredited, but you'd be surprised. For example, Yale doesn't have accreditation on their biomedical, computer science, environmental engineering, and engineering physics degrees, which is shocking, right? It's Yale. And there are several colleges that are like that where they don't actually have accreditation. With certain degrees like computer science, it doesn't really matter so much. They just want you to have coding experience. But with a lot of engineering, civil, mechanical, those all really, it does matter. The good thing, I guess, is that it doesn't really matter if you're going to go to graduate school. No one cares if you're going to do research that, like, if you have, you know, you fulfilled this requirement of this bureau. They just matter. It just matters that you can do research. But definitely, it's better to have the backup plan of being able to go and get a job immediately if you decide that you don't want to do graduate school, or you don't want to get a medical degree, or whatever. It's just good to have that, and that's at least what I would recommend. And then secondly, if you really want to be a good engineer, you need to get certified as an engineer. There's a lot of different types of certifications, but usually, or I would say they always require a 4-year degree in some sort of exam. And the only way you can be sure that you will have seen everything on these exams is if you went to an Abbott accredited university program. So again, I can't stress this enough. Just go to the website of whatever college you're looking to apply for or apply to in engineering and make sure that they have Abbott accreditation, because if they don't, you should at least, you know, I don't know. Just be careful is what I will say. Anyway, that's my talk. Thank you so much for listening.
Hello, my name is Sam Lyons, and I'm going to be presenting on video games, their design and development in general. I'm going to start off by talking a little bit about the industry of video games as a whole, then getting on to why people play video games, and getting into specifics of what it takes to develop a game and what careers look like within the video game world. And finally ending with, if you're curious about how to get started right away, these will be some tips. Awesome. Okay. So I think there's a lot of stigma surrounding the video game industry in general. You know, people think video games are a waste of time, and I'm not to say that's not the case, but I would like to clear up a few misconceptions. The first is that video games are a $140 billion industry. That's what they were in 2019. Whereas the movie industry combined for a total of $42 billion and the music industry for $20 billion. These are global numbers, so across the entire world. And if you're not that great at math, that's over double the value of both of those industries combined. A little snapshot within the video game industry is that on opening weekend, between the movie industry and the video game industry, the top grossing movie ever for opening weekend was Avengers Endgame, which came out a couple of years ago, and it grossed $860 million. Whereas Grand Theft Auto 5, which is a video game that was released back in 2013, made over $1 billion in its first 3 days. About $840 million of that came within 24 hours. So there is quite a big demand for video games across the world. And now, specifically talking about gamers in the US, what do they look like? A common picture that comes to mind is, a young teenage boy, playing on his Xbox in his basement or something. But the average age of a US gamer is actually 35 years old. And only about 60% of gamers are men, the other 40% being female. And a surprising fact is that on average, US gamers play about 7.6 hours per week. So that's, a little over an hour per day, which, if you think about it, can be quite a bit. And only 29% of US gamers are actually under the age of 18. So yeah, there's, a whole 71% out there who are actual adults in society playing video games. So one quote I want to bring up from Carl Jung, who's a Swiss psychiatrist and the founder of analytical psychology, is that one of the most difficult tasks people can perform, however much others may despise it, is the invention of good games. So, games are an integral part of all known human cultures. Digital games in their various formats are just a new expression of this ancient method of social interaction. We can think back to, any games you play as a kid that have been passed down from generation to generation. Those are all games. Creating a game is a challenging task. It requires a playful approach, but a systematic solution. You have to be an engineer, an entertainer, a mathematician, and a social director, in order to create a viable game. Yeah, and the role of a game designer is to craft a set of rules in which there are means and motivations to play. So why do people play? Why do people play video games? I think it's an important question to ask. And actually, Nick Gee in 2006 asked this question and came up with a few different answers for it. He had 10 total reasons people play games, but he broke it down into 3 main categories: achievement, social component, and immersion. So achievement in video games, you can think of that as, the desire to gain power or progress rapidly, accumulate in-game symbols of wealth or status, anything along that front. The social component could be anything, as simple as casually chatting with other players, working as a team, or creating, long-term meaningful relationships with others through this game or whatever game. And the final component is immersion. So being fully immersed into a fictitious world as a character with their own wants and needs. Discovery, role-playing, escapism, anything along those lines. So shifting gears a little bit, I just want to take a moment to look at 2 drastically different games and figure out, why we call them games. Because obviously a card game is very different than a board game, which is very different from a video game and a trivia game. But there is something that they must all share because we clearly recognize them as games. So if they don't share the same structure, then what do they share that makes them games and not 2 different forms of entertainment? So the first is players. Both describe experiences designed for players. And this sounds like a simple distinction, but what other forms of entertainment are designed to demand active participation by their consumers? Music is one example. Musicians participate in creating the experience of music, but the primary consumers are the audience, not the players. And similarly with dramatic actors, they participate in the experience of a play, but again, the experience is primarily created for the audience. The next clear distinction is that both of these games lay out specific goals for the player. So in Go Fish, that goal is to be the player who makes the most books, which are sets of 4, I believe. And in Call of Duty, it's whoever receives the highest score on the scoreboard. For those of you who may not know what Call of Duty is, it's literally just a first-person shooter game. it's quite, I think it's Fortnite or anything along those lines is pretty similar to Call of Duty. An important point about this is that because there are specific goals for players, that's pretty different, again, than other things that we participate in. When you watch a movie or read a book, there's no clear-cut objective presented for you to accomplish during the experience. Obviously, the characters in the book or movie have things that they have to do, but we're talking about, humans themselves, players that are partaking in this experience. So the objective is a key element without which the experience loses much of its structure, and our need to work towards the objective is a measure of our involvement in the game. So what I mean by that is, in life, we set out our own objectives and goals and work as hard as hard as we feel necessary to achieve them. If we don't accomplish all of our goals in life, we can still have a successful life. But video games demand some sort of objective or goal, or at least progress towards that, to create a viable experience. The next is procedures. Both games have detailed instructions on what the player can achieve towards the objectives. Pretty simple, it's just the rules of play, whatever that is. Next is, resources. So in Go Fish, the cards of each rank are valued. And in Call of Duty, the weapons, their ammunition, power-ups you can get for your character are all valued in different ways. And these objects are made valuable because they can help the player achieve their goal, but they're made scarce by the system, by the designer, whether that's there are a limited number of cards in Go Fish, or someone specifically programmed power-ups to be very infrequent in Call of Duty. A next note is that both games lay out specific objectives for their players. And the problem for the players is that these objectives are tended to be put behind different barriers that deter them from accomplishing these goals. And that conflict, it can be between you and the system of the game, or between you and another player. It's just any form of conflict that the players work to resolve in their favor. Next is boundaries, only in the sense that these rules and goals only exist within the context of the game. You're trying to make sets of 4 in Go Fish, but that's not something you need to accomplish to be successful as a human in life. So all of these objectives and procedures only exist within the boundaries and context of the game. And lastly, a final similarity between both of these is that their rules and constraints have the outcome of all the rules and constraints is uncertain, though there is a certainty of a measurable and unequal outcome of some kind. So there's a clear winner or loser, etc. In the sense that you might win, someone you're playing with might lose, you both might win, the game might lose, anything like that. And I know that was a lot. I'm sorry I threw that all at you, but I just thought it was important to really dive in for a moment about how vastly different video games can be from other games and games in general. So next, I just wanted to lay out essentially a step-by-step process of what it takes to do game development. Again, just as a reminder, the role of game design is to craft a set of rules within which there are means and motivation to play. So the first step is coming up with a high concept. Now, this is literally a general idea that you're coming up with. You're like, I want to make this game that does this. You should be able to say this in a couple of sentences, no more. It should just be the very brief outline for the game. The second step is your pitch. So this is your idea in a summarized form that best communicates ideas and goals you have for the game. The next is, it's a concept where you outline and describe all the aspects of the game: story, demographics, risk analysis, anything else that has to do with the video game as a whole. Next, you get to go into the game design document, it includes all the aspects tied to actual gameplay. And like what happens in each particular case, the rules, objectives, procedures, how the player interacts with these things, all of that. The next is actually creating a prototype. If you're lucky to get to that stage, you just create a quick mock-up of what your game is going to look like. And it should be something, ideally it's a vertical snapshot of your game, meaning that your prototype is not a bare bones outline of the entire game. It is one short moment of your game with all of the pieces of that moment laid out and included. So it would be like, for example, like one part of one level in a video game or something. It should just have all the elements that you want to include in your final game, but just a shortened version of that. And finally, the last step is production. And that includes the full fleshed out design of everything you have, level creation, and actual programming. This is where 3D modeling happens if you're making a three-dimensional game, audio work, and actual coding of the project starts. And so I just want to kind of end, because I'm trying to stick to the time frame we have, is talking about a few different game development careers that you could be involved in. And one thing I'd like to note about these is that you don't need a college degree for most or some of these. So if that's something you're considering down the line, just realize that. Obviously, some of them are it's more helpful to have a deeper understanding later on the line, but much of video game work is about creating a portfolio to show what you've worked on before. And if you get in the industry, it's pretty easy to stay in there. But these are just some broad categories of different careers you could take within the video game industry. A designer, so this is a creative director. You're the one who comes up with the whole game development document and high concept pitch for your game. You're the one, like, this is the game you want to create, and you're responsible for all of that. A writer is not necessary in every game. It's just if you have a story in your game, writers can be helpful to set out how that game is going to, how the story in the game is going to play out. Programmer is probably the most common career in game development. You're code monkeys. You're the people actually turning the ones and zeros Julian was talking about into an actual game, an experience that players can interact with. The next two are different forms of artists, visual and audio artists. So someone who does the modeling of everything that you see in the game, or the music and the soundtrack that you hear while you're playing the game. And the last two are part of game development, but they're much more broad and they're general in their scope. A manager, someone who oversees everything, make sure everyone is doing what they are supposed to be doing, is on task, and the business person. So, I just put marketing as an example, but any business side of game development you could think of. You could make the best game in the world, but if you don't have some form of marketing or someone to get that out there, no one's going to play your game. No one's going to see your game. And that's why that has become such an important part of game development in recent years. So a few notes. As someone who has tried game development myself, it's not an easy path. Don't think it is. You like playing video games. Video games are fun, but it's not the same as doing that. It's a pretty much a headache the entire time. But if you like that, you might really enjoy game development. A few tips I have that I think are helpful is start by trying to clone a game you've played. Keep it simple. The first game I ever created was a clone of the game 2048. As basic as it gets, just trying to see if I could isolate all of the different components that are required to make a game like the game 2048 and reconstruct them into a functioning thing. And it seems you might think, oh, that's pretty simple, but it's actually a really good exercise. And it's just much easier if you don't have much coding experience, because there are a lot of visual software that you can use to drag and drop a game into existence without writing a single line of code. Next piece of advice I would give is set realistic goals. So if you have an idea for a game, say you want to create the next Call of Duty or something, you want to make a first-person shooter with all the bells and whistles, cut it in half, then cut it in half again, and then cut it in half again, because it's remarkable how much time and energy it takes to do even the simplest things in a game. So just understand that if you're starting in game development. Another note is just mechanics trump content always. If your game is not fun to play, people are not going to enjoy it, even if you have the most beautiful game in existence, or if you have the best soundtrack a game has ever seen. It's not going to matter if your game's not fun to play. Finally, this is just kind of a core point for any part of the video game process, is create a minimum viable product first. And what I mean by that is boil your game down to your game idea down to the most essential elements. Do that, and then you can add anything else on after that. Yeah, so here are just a few pieces of software I would personally recommend if you're wanting to get started in this. Unity's a free game engine software where you can, it does require some coding, but there are some non-coding options that you can use, and it'll help jumpstart your game development quite well. Another is Krita, which is a drawing software, and Blender, which is a 3D modeling software. These are all free programs, so that's why I put them up here.